Let me introduce Shahbaz Abdul Khader. He is now a PhD student at the Robotics Perception and Learning Lab at KTH, Royal Institute of Technology. And he is being supervised by Professor Danica Krajic. And the title of today's talk is Learning Robotic Interaction Tasks with Stability Guarantees. So over to you, Shahbaz.
All right, thank you for the introduction. So I'm going to talk about our recent work on achieving stability in reinforcement learning. So in this work, we do not focus on grasping or perception, but rather on the control of the manipulator. So we begin by understanding interaction tasks, also known as contact-rich manipulation tasks. So manipulation can be classified based on the presence or absence of contacts. So contact-free manipulation is a purely kinematic affair and can be solved by generating appropriate trajectory and closely following that. This approach breaks down in the contact-rich case, mainly because it's almost impossible to plan a perfect trajectory that will avoid all unnecessary contacts. And contacts, when they do occur, will give rise to complex and unknown dynamics. Now it's not so obvious on how to synthesize control policies for these kind of tasks. A classical benchmark for interaction tasks is a peg-in-hole problem, which we also use in our experiments. In this problem, the robot is expected to insert a peg into a low clearance hole. As you can imagine, this will generate unexpected contacts. So we propose to use reinforcement learning for learning interaction tasks. In reinforcement learning, the robot performs a number of trials that produces data and which can be used to optimize and update the current control policy. And this will go on for a number of iterations until the policy converges to the correct value. This is called model-free reinforcement learning, where the data generated from trials is directly used in the policy optimization. The other variant is the model-based reinforcement learning, where an intermediate step of building dynamics model is also incorporated. Regardless of model-free or model-based, what makes reinforcement learning really interesting is that it only requires a reward function that describes the task. There is no need to supply it with any nominal trajectories, feedback controllers, or any dynamics model. So this may sound as an ideal solution for our problem, but it has some weaknesses. For example, it may produce some completely unpredictable motions. So here, this is exactly what happens, where you can see a robot making very unsafe and unpredictable motions at an early stage of reinforcement learning of a particular task. So clearly, this kind of behavior is unacceptable in a real-world scenario. We can make progress by borrowing the concept of stability from control theory. A stable system is one in which all trajectories converge to a single point. And this property, to a great extent, can help avoid unpredictable motions. And we would like to have this stability property throughout the reinforcement learning process. And that's what we call as all-the-time stability. So now the question is how to incorporate stability into reinforcement learning. So the most widely used notion of stability is that of Lyapunov stability. A traditional Lyapunov analysis would include, in addition to the policy, the control policy that is under consideration and the dynamics model of the process, a Lyapunov candidate function is proposed with the hope that the combination of the three will lead to a stability certificate. So here, notice that different degrees of stability is possible. What is really important to understand here is that the three quantities which are involved in Lyapunov analysis usually have analytic forms. The Lyapunov analysis itself is done manually as a mathematical proof. So since the dynamics model is involved, it's reasonable to assume that some kind of model-based reinforcement learning is the way forward. However, we run into three problems. First of all, model learning of interaction tasks is extremely difficult because of the complex nature of contacts. And then typically, the learned models are usually non-analytic forms, for example, neural networks. And finally, it's not obvious how to automate Lyapunov analysis. So these are very hard problems in general. We take a smarter approach where we manage to avoid these. But in order to get there, first, we need to understand a basic property of robot-environment interaction. Here, the key concept is passivity, which is closely related to that of stability. And it simply means an object cannot create energy. So most objects in the environment are passive because they do not have a power source. The robot does have a power source, but it can be made to appear as passive through control. So what this says is that if a manipulator is made stable and passive in isolation, then it is free to interact with any passive object in the environment, completely unknown, and still retain stability. So this has powerful consequences. Now we are back to a familiar territory where we can do more traditional Lyapunov analysis, mainly because the analysis is limited to the manipulator in isolation, in which case the dynamics model is completely known and has an analytic form. Neither do we have to consider any contact dynamics, nor do we have to learn it. And furthermore, both the policy and the Lyapunov function may be formulated with analytic forms. There's one more ingredient that needs to be in place before this can work, and that is a requirement that the Lyapunov function and the control policy are parameterized with the same set of parameters. This is helpful because now the Lyapunov analysis would produce some kind of stability conditions on this shared parameter set. And as long as this condition is satisfied, any potential model-free reinforcement learning algorithm could improve the policy and find a solution without having to do any reanalysis. So effectively, we have converted a very tough problem into a much simpler one where half of it is solved in an offline manner through a traditional Lyapunov analysis, and the other half with an online constrained reinforcement learning. So it turns out that the offline part of the problem is readily fulfilled by an existing method, although it was not proposed for such a scenario. So our focus has really been on the reinforcement learning part. And for this, we adopted the approach of evolution strategy, which is a global optimization method. In evolution strategy, the solution set is represented as a sampling distribution, which is then continuously refined through a process of sampling and evaluation. In the context of reinforcement learning, each of these samples corresponds to a reinforcement learning trial. So what is interesting here is that we designed the sampling distribution in such a way that the stability conditions are satisfied inherently. The conditions in our case were positive definiteness for most of the elements in the shared parameter set. So all we had to do was to model those elements with a special distribution called the Weishart distribution, which is a distribution of positive definite quantities. So here we see some results on the peg-in-hole problem. So notice that even in iteration 0, before any learning has occurred, the robot is exhibiting stable behavior. In other words, the motions converge to a particular point. And in about 300 trials, the robot learns to do very consistent insertions. And below the video, you can see some simple stability tests, which is done in simulation for exactly the same problem, where we randomly initialize the initial position of the robot. And what we can see here is that even before any learning in the 0th iteration, all of those randomly initialized trajectories converge approximately to the goal. Well, it didn't really get all the way to the goal. In other words, it didn't succeed in the insertion. I mean, if it did, then we wouldn't need reinforcement learning. So here the big message is that the task may not be successful, but we can trust the robot right from the beginning, and not doing any harmful or unpredictable motions. So I would like to conclude by pointing out that reinforcement learning is important for interaction tasks because there's not many other alternatives, and some form of all-the-time stability is essential if you really care about real-world deployment. We believe that the stable reinforcement learning of the peg-in-hole problem may be unprecedented. This is noteworthy because the pigeonhole problem is a classical problem in robotics. And so far, the limitation is that we use specialized policies which have analytic forms, and this may not be flexible enough for a wide variety of tasks. And more importantly, it cannot incorporate high-dimensional observation input. So this leads us to the question if such a on all the time stability reinforcement learning is possible using neural network policies. So with that, I end my talk, and thank you for listening. I'm looking forward to the Q&A session.